Welcome to this explainer. Today we're taking those big, abstract, object-oriented programming theories and turning them into concrete, exam-ready C++ code. If you've ever felt like OOP concepts are just, a bunch of floating ideas without a practical anchor, well, you're in the exact right place. We're going to lock those ideas down into code you can actually use. Let's get into it.
Here's our roadmap for this explainer. We'll be looking at encapsulation and abstraction concepts, objects, classes and access, constructors and class types, structures versus C++ classes, data types and modifiers, and then we'll wrap it all up with our key OOP programming takeaways.
All right, let's dive right into Section 1, Encapsulation and Abstraction Concepts.
Take a look at this. It beautifully illustrates encapsulation. Think of it literally like a medical capsule. Encapsulation is essentially the process of combining data members, so your variables, and the member functions that manipulate them, all into one single unified block called a class. But, why do we even do this? Well, it's all about data hiding. Think of a company's financial department. They handle the money and strictly restrict direct access from, say, the sales team, right? Encapsulation protects sensitive data in the exact same way. If the sales team needs financial data, they can't just barge in and grab it. They have to go through the proper channels. In our code, those proper channels are your class functions.
Now, on the flip side, we have abstraction. Abstraction is kind of like looking at a car. When you're sitting in the driver's seat, you only really need to see the relevant interface: the steering wheel, the gas pedal, the brakes. That's the driver's view. It intentionally hides the overwhelming complexity of the engineer's view underneath the hood: the pistons firing, the electrical routing, the transmission gears, the whole shebang. Abstraction selects only the relevant details to show, acting as a really critical tool to help us cope with complexity.
Let's put them side by side, because honestly, this is a massive exam-relevant distinction. Abstraction solves problems at the design or interface level. It's like the architect planning out the building. Encapsulation, however, solves problems at the implementation level. It's the builders actually putting up the physical walls to keep people out of the secure rooms, typically using access modifiers like private, protected, and public.
Moving right along to Section 2, Objects, Classes, and Access. First things first, you absolutely have to remember the fundamental difference between a class and an object. A class is really just a logical blueprint. It's an idea. And because it's just a template, creating a class consumes absolutely zero memory. It only becomes a physical entity, an object that actually eats up heap or stack memory when it's instantiated. So the class is the blueprint of a house, the object is the physical house you can actually walk into.
Now, because our data is safely hidden inside that theoretical capsule we talked about a minute ago, we need a way to interact with it safely, right? That's where getter and setter functions come in. Think of them as the official secure doors to interact with our variables. A setter sets or updates a value, and a getter fetches or retrieves a value. This right here is exactly how we write secure, robust C++ code.
Just looking at this code snippet, notice how the salary integer inside our employee class is explicitly marked private. This means the main function at the very bottom cannot simply say, my object.salary equals 50,000. That is strictly illegal in OOP. Instead, it forces the main function to rely entirely on the public setSalary method to pass the value in and the getSalary method to safely read it back out.
Okay, here's a huge trap you need to avoid in your assignments. We have a circle class with a private radius. Down in the main function, the code tries to directly assign 1.5 to the object's radius. Trying to bypass those setters and directly modify a private variable like that, it immediately triggers a fatal compile time error. There's no way around it. The compiler will physically stop your program from running just to protect that data.
So the absolutely crucial point here is this ironclad rule. Private members are completely invisible to the outside world. They can only be accessed by the functions living inside that exact same class. This ensures total data security and, practically speaking, prevents accidental modifications from other parts of a massive software project.
Let's look at the fix. By shifting our logic to use the public compute_area method instead and passing our 1.5 radius into the function as an argument, we are respecting the class's privacy boundaries. The public function takes the data, interacts with the private variables for us, and boom, our code successfully compiles and outputs the area as 7.065.
All right, Section 3, Constructors and Class Types.
So what is a constructor? It's a special public member function, and you can always spot it because it shares the exact same name as the class itself.
like here where it's called car. Notice it has absolutely no return value, not even void. Its entire purpose in life is to initialize default data members the moment an object is created. Oh, and a quick pro tip. If you forget to write one, the C++ compiler will actually silently generate an empty default constructor for you behind the scenes. Pretty handy.
As your programs start growing in complexity, you won't just stick to simple classes. You'll utilize concrete classes that can be directly instantiated into objects, say a specific cat or dog, but you'll also create abstract classes. An abstract class features what's known as a pure virtual function. That's a function with no code in it at all, just a declaration setting it to 0. Because of this, abstract classes cannot be instantiated. They act purely as generalized templates for inheritance, kind of like a broad animal or vehicle category.
Next up, Section 4, Structures versus C++ classes.
Historically speaking, back in the older C programming language, structures were very basic. They were pretty much limited to just holding different types of data together. You couldn't put functions inside them, but C++ gave structures a massive upgrade. Modern C++ structures can include member functions, constructors, direct initialization, and even static members. Honestly, they operate almost identically to classes today.
So you're probably wondering, if they're almost identical, why use both? Well, the ultimate exam takeaway here is default security. If you create a struct and forget to type an access modifier, the struct defaults to public. That leaves all your data completely vulnerable to outside interference. But if you make that same mistake in a class, it defaults to private, keeping your data safely locked down. Plus, classes are generally preferred when you're dealing with complex inheritance and large-scale architectural design.
Let's jump to Section 5, Data Types and Modifiers.
Grasping the byte sizes of primitive types is absolutely critical for writing memory-efficient C++ applications. For instance, an integer typically takes 4 bytes of memory, whereas a double, which we use for larger decimal numbers, takes up 8 bytes. A Boolean, or a standard character, just 1 byte. Knowing these sizes really helps you design classes that don't just wildly waste system memory.
And to optimize your memory footprint even further, you can use type modifiers. Say you know a variable will never, ever be negative, like an employee ID. You can use unsigned int to restrict it to positive numbers, which effectively doubles your positive range. You can also use short for small numbers or long for massive ones. And here's a really neat trick for readability. You can employ the typedef keyword to give standard data types a custom alias. So you could type typedef int marks, and then simply declare variables as marks instead of int. It just makes your code read so much cleaner.
Finally, we arrive at Section 6, Key OOP Programming Takeaways.
We've covered a lot of ground, so let's cement these structural patterns in your mind. Remember, classes default to private security, while structs default to public. Constructors always share the class name, and they return absolutely nothing. Encapsulation builds the walls at the implementation level, while abstraction simplifies the interface at the design level. Relying on constructors for initial setup and getters and setters for data access, that is the undeniable blueprint for robust, professional, object-oriented programming.
I want to leave you with one vital thought to really test your understanding. If you decide to abandon the protection of private access modifiers simply because it's, a bit faster to write public variables, what exactly happens to the integrity of your code? Think about the accidental overwrites, the unauthorized access from other software modules, and the absolute nightmare of debugging a system with zero internal security. It's a disaster waiting to happen. So, stay secure, keep your data private, and happy coding.